We've been talking a lot in this section about limits. Thinking back to Calc 1, right after we talk about limits in Calc 1, we talk about continuity. And so we should probably do the same here. So here's a definition. What does it mean for a function of two variables to be continuous at a point? Well, it means same set of things that it's going to be for one variable continuity. The function is defined at that point. That was something we had before. The limit as the limit of the function as you get close to that point exists. And that sounds familiar. And these two things need to equal each other. And in fact, you can kind of summarize continuity by just taking this third bullet point here. Because if you say the limit is xy goes to x naught y naught of f of xy is equal to f of x naught y naught, you know, the fact that you're writing this implies that f is defined at x naught y naught. The fact that you're writing this here implies that the limit exists, that they equal each other. So really, this is the summary here. And again, to reiterate myself, these are essentially the same three conditions as we had about continuity back in Calculus 1. And so this is the definition for a function to be continuous at a point. The last little thing here has to do with function is continuous if it's continuous at every point of its domain. And so, so we should discuss continuity of f of xy is x squared over x squared plus y squared. Here's our example for this. Now, just as a reminder, we showed in the previous video that the limit as xy goes to 0, 0 of this function does not exist. But you also note that the domain is all xy other than the origin, 0, 0. Because if we plug in 0 and 0 in for x and y, we get 0 over 0, we get something that's undefined here. So this function here is not continuous, CTS continuous at 0, 0, but 0, 0 is not in the domain. And in fact, it doesn't take too much thought to see that actually f of xy is continuous, and I'll put in parentheses, on its domain. So the only time that we can have trouble here is if x squared plus y squared is equal to 0, which is when x and y are both equal to 0. If x and y are anything other than 0, 0, this fraction is going to be defined, and the limit as you get close to any point other than 0, 0 will just be, you can just evaluate by substitution. So this function is continuous on its domain. Okay, so that's a little discussion here about continuity. I want to do one more thing in this video, which is, let me get here to this example here. This one, yeah, so I say here, determine whether or not the following limit exists. And it might look something like this. So let's just observe here that if we plug in 0 in for x and y, we get 0 over 0. So we might be thinking, okay, so 0 over 0, so we have to do something else. We could try the polar form stuff. We might think, okay, this y is equal to mx trick here is pretty slick. Remember, the y is equal to mx trick is associated with this two-path test for non-existence of a limit. So, you know, what we're going, you know, to apply this, we can find two different paths into the origin in this case, and the limits along those two paths are different from each other. We can conclude that the overall limit does not exist. So let's go ahead and try y is equal to mx. Okay, so we try y is equal to mx. We have the limit as, this is now just going to be the limit as x goes to 0 of x squared times mx over x to the 4th plus mx, excuse me, mx quantity squared. This simplifies down to x cubed times m over x to the 4th plus m squared x squared. And if you're paying attention, we can factor out an x squared from the numerator and the denominator. So that would be x squared times xm over x squared times x squared plus m squared. Those x squareds cancel. What are we left with? Limit as x goes to 0 of xm over x squared plus m squared. So let's think about this. Again, m is any real number. What we get here, we plug in x is equal to 0. The numerator is 0. The denominator is the denominator is going to be m squared. So let's just assume here that m is not equal to 0. We're going to end up with this limit will be 0. So this is kind of interesting that this says that every straight line path going into the origin other than m is equal to 0 is going to be is going to give us a limit here of 0. But there's so it seems like the limit along every straight line path gives us 0. And so you might be tempted to say, oh, okay, so throw up your hands and say, I'm checking infinitely many different paths here, and the path along every straight line going to the origin gives me the same number, gives me 0. So this limit must be 0. But it turns out that this isn't enough. We have to do more work here. This is one of those things where we can't just say, oh, we've checked lots and lots of paths and they all give us 0. That's not enough. So let's try something else. What happens if we try things of the form y is equal to ax squared? So instead of doing straight line paths into the origin, so y is equal to ax squared. So like this might be y is equal to x squared. This would be a is equal to 1. Y is equal to 2x squared. This would be a is equal to 2. What happens if we go in along these parabolas? What happens if we go in along these parabolas to the origin? So in this case, what happens is, well, let's make the same replacements there. So we're going to have the limit as x goes to 0 of x squared times y is ax squared over x to the 4th plus y squared is ax squared squared. And this is the limit as x goes to 0 of upstairs is ax to the 4th over x to the 4th plus a squared x to the 4th. And it looks like we can factor out an x to the 4th from both the upstairs and downstairs. So we can cancel this out. And what do we have? The limit as x goes to 0 of a over 1 plus a squared. And this is a limit of a constant. It's just that constant. So this is something that this is going to depend on a. So if a is equal to 1, if we're moving along this one, the limit as x goes to 0 of our expression is going to equal 1 over 2. But if a is equal to 2, the limit a is equal to 2, the limit x goes to 0 of a over 1 plus a squared. This is going to equal 2/5. And these are not equal to each other. And so we conclude by looking at these parabolas, the answer here is no. This limit does not exist. So what's the point of this video? The two-path test is genuine paths, any possible paths. They can be as weird as you want them to be. And so it's not just enough to, like we did in this previous video, y is equal to mx. That was enough in this video. But even if all of the straight line paths agree, there's many, many other possible paths. And so parabolic paths give you a disagreement, and so this limit doesn't exist. Okay, I think that's an important lesson, and I think that's a good place to wrap things up. So here is a pre-class problem. I want you to show that this limit does not exist.